everyone, and thank you for joining us today to discuss GPU compute scalability and our hardware architecture for deep learning at Yahoo. My name is John Glover, and on behalf of Murad Barash and myself, we would like to present some of the hardware architectures we are working on to support deep learning at Yahoo. First, I wanted to give a little background on our team. The Performance Engineering Group, or PEG, is responsible for exploring and selecting current and next generation hardware technologies, as well as how to integrate them into our infrastructure at Yahoo. We determine the TCO for our usage of new products and work with vendors and internal properties to help them determine the best configuration for the value. We are responsible for setting the hardware technology roadmap for the company. We select which production servers to buy and what components they should contain. We also work with development teams to provide optimal hardware configurations based on benchmarking and performance metrics. We have an amazing lab located at our headquarters in Sunnyvale that does performance testing and certification for all of Yahoo's servers, server components, network devices, and security hardware. So the agenda today will cover the following areas: learning, humans versus machines. As a subset of the larger field of machine learning, we can briefly cover deep learning. And with the growing interest in image, speech, and object recognition, we see a shift from academia to mainstream. Next, we'll go over some of the uses of deep learning at Yahoo, which will take us into the software and hardware platform, and then some GPU scaling testing in our performance section. We'll wrap up with a little overview of what we're looking into in GPU compute next. If you've been following the buzz around artificial intelligence lately, you may have gotten the impression that machines will soon take over the world and destroy its human overlords. As technology continues to automate more and more of our daily routines, it's easier to understand this fear, especially when so much of how AI functions seems a mystery to most people. But like any intelligence, the accumulation of that knowledge has to be learned or trained. And it's in how we learn, how we process information to make decisions, that we can start to demystify how AI functions. AI has an objective and uses the information provided to make a decision toward that objective. This is a process the human brain does, but only at a certain scale. We can use AI to automate or assist us with tasks, but it only works as well as we can train it. One example of AI assist we've trusted some automation to is the fighter jet. Jet planes required human decision making and fine tuning at more than 3 times the rate of propeller driven aircraft. The key to successfully flying a jet aircraft was learning what to outsource to the automated systems and what to retain for human management. Today, F-13 pilots have taken this to a new level, as each pilot is now equipped with their own personalized F-35 AI. And when assigned an aircraft, the aircraft receives the AI specific to that pilot and their mission. So each aircraft operates differently, trained to each pilot's preferences and to the specific mission for that pilot. But this is still far from a fully automated, unmanned aerial vehicle. The human pilot truly controls what the jet should be doing instead of what it can do. The amount of compute it would take to replace the human factor in all lessons of warfare is unknown, but becoming somewhat fathomable. Evolution has encoded the results of a huge environment-dependent optimization in the structure of our brains. That structure has refined how we interpret the world around us and allows us to learn and accumulate more knowledge. This is a result of nature that AI would have to somehow replicate. In an attempt to optimize how we teach or train machines, we have been looking to using what nature has already given us, emulating the brain as much as possible. Where deep learning starts to emulate the brain's decision process is in its implementation of neural networks. These biologically inspired variants of machine learning programs derive from the programmers trying to emulate the sequence of events and interpretations that occur for a biological function to perform its task, such as recognizing an object. The more we understand the process of how our brains correlate the information around us to make the decisions we do, the better we can emulate that process in code. In Google's TensorFlow, we are even seeing more optimization efforts in how we orchestrate these computational elements to better assist the workflow through these neural networks. Deep learning is a machine learning method that's particularly useful in helping computers sort through and recognize user-generated data, and one of its most exciting use cases is where images are concerned. As such, our Yahoo Deep Learning team built Cafe on Spark to help identify the billions of images posted onto Flickr's photo sharing website. With the growing interest in machine learning and deep learning as a way to enhance enterprise products, we're seeing a transition from studying machine learning and studying the algorithms around it. We're seeing that transition from academia into the technology industry, into mainstream. Google, Facebook, Microsoft have all been putting out a parallel compute framework or an orchestration for a framework in assistance to deep learning in enterprise. And as you can see, there's been a lot of really big innovations in how we use GPU parallel compute. In any case, answering the question of why academia hasn't made as big strides in deep learning mainly could be because machine learning researchers in academia don't necessarily organize themselves in the same way as those in industry, and because they often study the method more so than the problem. So this sometimes tends to lead to smaller research groups working in parallel, isolated from each other, or even in competition, whereas in industry, you'll see larger research teams working towards a common goal. Here we have two examples of how Yahoo is leveraging deep learning to enhance or add features to existing products to give our end users a better experience. One example is Flickr's auto tagging. This allows the pictures that are uploaded to Flickr to be auto tagged for subject. This leads to having better search results when searching for more abstract objects like a flower or a bridge. This has definitely increased people's usage of the product because now they're finding new and interesting ways to correlate what they're doing based on the image recognition that's just happening automatically when they're uploading their pictures. Another example would be Yahoo Esports. Everyone knows that competitive video gaming has been growing in popularity over the last decade, but not only has playing been growing in popularity, but watching and observing these gamers has been growing as well. Yahoo Esports covers the competitive gaming area as well as using deep learning to analyze the playback videos of these matches and start being able to pull highlights out for their fans to be able to quickly go to their favorite user and see some of their best or favorite moves. This is just one other way how deep learning is being used to enhance a existing product to give a better end user experience. Yahoo's interest on deep learning really started to gain traction with the idea of making the search function on Flickr more useful so that it could pick out suitable images based on more than just the descriptions and tags users write down when they're uploading pics. Deep learning software is able to learn and recognize the specific common characteristics of certain kinds of objects, animals, and landscapes. Last year, Yahoo's deep learning team built a library called Cafe on Spark to perform deep learning on our Hadoop cluster, which enables big data analytics. Now it is available for anyone to use under an open source Apache license on GitHub. Cafe on Spark supports deployments on generic x86 architecture chips or graphical or GPUs. It can be run on cloud infrastructure or on your company's own commodity hardware. Servers running this distributed software can be interconnected over Ethernet or with a faster InfiniBand fiber channel connection. It's available as a third-party Spark package. Internally at Yahoo, the software has been used for Flickr, spam detection, account security, and content recommendation. Documentation for Cafe on Spark is online. This next slide contains a few press listings from the deep learning team's work on Cafe on Spark. Now let's go over the hardware platform that we used for deep learning. Since our objective was to create a highly parallel computational workstation, we followed 3 different criteria. We decided that we needed to determine the best server selection and the best compute unit for that server selection, as well as a network interface that is going to allow us to scale past what we can do within the single server. That being said, we also had power constraints for how much power we could actually draw in a single rack. So first we started with the server selection. Looking at what was available in the industry at that time, we came across the Dell C4130 because it had the ability of running up to 4 Tesla K80 GPUs in one system. That allowed us to really maximize the amount of compute we could get into a single system and make that as an efficient of a power draw for those GPUs in the system. So seeing as we wanted to maximize the amount of parallel compute in each system, we did look at the Tesla K80. The Tesla K80 was the premier parallel GPU compute option at the time, and it was certified for use in the C4130, which means we could get up to 4 in a single system. This allowed us to scale our previous training of single CPU up to 4 CPUs in a single system. Now that we had the max performance of a single system, we decided that we needed an interconnect layer to be able to scale out GPU compute across the network when we need to scale past what a single system can do. That's when we started looking into what interconnects would support a direct memory access layer such as RDMA, and working with Mellanox, they recommended a ConnectX-4 card, which actually also supported GPU Direct, which is another protocol on RDMA that NVIDIA was using to increase the throughput of memory access by having direct GPU memory access instead of just having to go through the chipset. So with those selections, we were able to start designing the architecture. The data center architecture design was based mainly on power constraints that we had for a rack of systems. Seeing as we were able to get up to 4 Tesla K80 GPUs in a single system, that created a very high power draw. We were seeing, at max of up to 1600 watts. So we rated these systems for 1600 watts with a 1600 watt power supply. Seeing as our racks were limited to 12 to 15 kilowatts, we were really only able to stage 8 of these systems per rack. And that's basically due to the power constraint. Now, once we were able to stage these in the racks, we decided to centralize the InfiniBand interconnect that was going to support RDMA and GPU Direct. So as you can see in this slide, we have our initial topology of 24 systems is spread across 3 racks with our InfiniBand switch, which is the hub for the GPU Direct shared memory layer, being in the center, so as the cabling to each of the systems was basically the same length. So this topology allowed us to some room for expansion, since we are since we were using 24 systems, and there's a 36 port InfiniBand switch, so essentially expandable by another 12 systems. The configuration of the server was important because we wanted to make sure that we were getting a server that was going to give us max bandwidth between all 4 of the GPUs. The Dell C4130 had several configurations you could make based on the number of GPUs you wanted to add to the system. Since we wanted to basically a high performance, max throughput, and scale out system, we went with four GPUs. So this is the basic system GPU topology that we have in each C4130 system in the cluster. As a way to validate our decision of using GPUs instead of CPUs, we analyzed the potential peak performance of SGEM, which is a single precision general matrix multiplying benchmark, on Ivy Bridge dual socket CPUs, and compared that to the NVIDIA Tesla K40 for 2 and 4 GPUs. We understood how much optimization space is left for SGEM, so we had a performance offset. But according to our results, you can see that the estimated performance of SGEM using CPU is 0.7 teraflops, compared to the 5 teraflops we're seeing with the dual Tesla K40, and the 9.5 teraflops, almost double, that we're seeing with the 4 Tesla K40s. This was just a benchmark to really help us confirm that for this particular workload we could scale quicker and more linearly with GPUs as opposed to CPUs. NVIDIA's GPU Direct over RDMA is a technology which enables a direct path for data exchange between the GPU and third-party peer devices using standard features of the PCI Express bus. Examples of some third-party devices include network interfaces, video acquisition devices, even storage devices, storage adapters, and medical equipment. But enabled on Tesla and Quadro class GPUs, GPU Direct over RDMA relies on the ability of NVIDIA GPUs to expose portions of device memory on a PCI Express base address register region. RDMA is a direct memory access from the memory of one computer into that of another without involving either one's operating system. This permits high throughput, low latency networking, which is especially useful in massively parallel compute clusters. We compared the performance gains for some workloads using GPU Direct technology from NVIDIA. In some benchmarks, we see up to 9, almost 10% improvement. The percentage is representing the gain that we see in the different metrics. But as you can see from this slide, for lamps, we're seeing up to 3% difference in steps per second. And for the amber, cellulose, and factor 9 benchmarks, we're seeing as high as almost 9% performance improvement by using GPU Direct. We performed a quick Cafe on Spark training with a Haswell CPU, the E5-2680V3. This dual-socket CPU had 12 cores and 24 threads. The YCafe training on CPU took about 65 seconds using Haswell. For the GPU mode, we were using the NVIDIA Tesla K80 with 4,992 CUDA cores, which is roughly 2,500 per GPU. The memory size is 24 gigabytes for the card, and can roughly do about 480 gigabytes per second. The peak single precision floating point performance is about 8.74 teraflops. So that got our training time down from 66 seconds on CPU down to 25 seconds on GPU. Next, you can see the GPU scaling performance testing we did while training image recognition with AlexNet and GoogleNet. There's been a lot of exciting movement in the GPU space in just the last year that we've been working on GPU performance scaling. One of those areas is the GPU architecture. We had been standardizing scaling performance on the Kepler and Maxwell GPU cores that NVIDIA had been supporting for the last few years. And that was a lot of our models were based on that architecture. So when the announcement of the Pascal architecture came out from NVIDIA earlier this year, it really got us thinking about, okay, what is this new architecture going to mean for what we're doing right now? How can we use it to expand on what we're doing? Or is this going to bring a new use case? Is this going to basically not invalidate, but end of life previous versions of GPU compute before it? Those questions definitely came up as we started getting more information about the Pascal core and how it would be packaged. The first packaging of the Pascal core that we had seen for enterprise market was the announcement of the DGX1. This is based on combining two 20-core Xeon E5 V4 processors with 8 of the Tesla P100 cards. The Tesla P100 cards are interconnected with NVIDIA's NVLink, which is going to improve the shared memory bandwidth, and they are also interfaced to the CPUs through a PCI switch, which allows all 8 of the cards to get full bandwidth when accessing them. So this particular unit is boasting 170 teraflops of compute performance, but we were unsure as to how it would scale when trying to interface these over the network. So the next item that was just recently announced that caused us to kind of reevaluate what the DGX was doing was the announcement of the PCIe version of the Tesla P100. So instead of being packaged in an appliance and having that have a limit of performance, the P100 PCIe version would basically allow us to scale similarly to the way we've done with the Tesla K80s. Now we still need to work with vendors to validate systems that will be able to support the P100. And within the P100, There is a straight PCIe version, and there's an NVLink version that is allowing that proprietary interconnect for boosting the shared memory. So these are definitely two areas that we will be looking into. Since NVIDIA officially announced the Pascal-based Tesla P100, they've been posting theoretical performance numbers, and we're seeing, and they're showing that they can deliver maybe 65% higher speed with around 2 times the transistor density, and basically they're doing this at 70% less power for the number of transistors that they're adding. So all these really add to more dense compute, and ultimately can contribute to reducing our training times, which becomes a defining metric for how much we want to scale out GPU compute. The next area we want to look into is the cloud computing of GPUs. We've done some looking into the offerings of GPU in infrastructure as a service models, and Amazon's AWS does offer GPU compute, as well as IBM's SoftLayer. They offer standalone GPU compute options, but we're not quite seeing the scale out options for highly parallel computational workloads. Now, what the value and demand is for that, we anticipate the demand is going to increase, but the cost of supporting in a scaling GPU compute environment like that may overshadow the usage. That's an area that we need to really find out what it takes to create a dynamically scalable GPU compute environment and offer that as a service. Just another area that we want to make sure that we're evaluating and seeing opportunity if it is there. So there you have it. That's our presentation on scaling performance of GPU compute. If you have any questions, Murad should be on Skype to answer any of the questions you guys have for the presentation. And we just want to say thank you very much for joining us. Thank you. Bye-bye.